Hello, welcome back. We're going to be doing an example of finding a difference of population means given two sample means. Okay, so in this example, let's take the vitamin D study example that we were doing before. We're doing a study on vitamin D levels of different parts of the United States. And in the study, blood samples of vitamin D for 36 people in Cleveland were found to have a mean of 50 nanograms per milliliter, and the known population standard deviation is 5. The blood samples of vitamin D patients in another location in Tampa, Florida, for 36 individuals in that sample were taken with a sample mean of 95 nanograms per milliliter, and there is a known population standard deviation of 6 nanograms per milliliter there. Now we're going to find the confidence interval at a critical value of 0.95, or the confidence level of 95%. Okay, so I think we've done a lot of these equations. Now we can continue separating the margin of error, but we can write everything out as it is too. Okay, so here let's combine the equation that we have in yellow and the equation that we have in green so that we see all of it together. Okay, so the difference in the first sample mean and our second sample mean is going to be added or subtracted to our margin of error, which we have as z sub c square root of the first population standard deviation over its corresponding sample size that was taken, plus the population standard deviation of the other sample size taken squared all over its sample size. Okay, now I like to think ahead here a little bit. Typically, I like to do the first sample size as the bigger mean. Okay, so between these two, we see a bigger mean in Tampa, Florida. Okay, and it's just because when we're subtracting a smaller number from a bigger number, we end up with a positive value. So it makes a little bit more sense when we're talking about averages, right? So let's get into that habit as well. Okay, so Tampa, Florida, I don't know, I'm going to put it as orange here. Okay, the sample mean is 65. We had samples from 36 people and a population standard deviation of 6 nanograms per milliliter. So let's start writing all of this out. Okay, sample mean 65. Population standard deviation 6. Sample size 36. Okay. Now let's look at, I'm going to sub 1 there. Now let's look at our second sample from Cleveland. And we're going to do that in green. Okay, 36 people as well. I'm going to make this note right now. They do not have to have the same sample size. That's just how we have it here. Okay. Mean of 50 and a population standard deviation of 5. So sample mean is 50, standard deviation is 5, sample size is 36. Okay. Last but not least, we have our z critical value, which we know is 0.95, and it's been the one that we've been working with a lot, so we probably already have it memorized as 1.96. Again, that's going to be calculated based off of the area underneath the curve. Please refer to section 7.1 for an in-depth calculation of that critical value. Okay, so let's plug everything in. Sample mean for our first sample is 65. Sample mean for our second sample is 50. We're going to subtract those two together, and then we're going to add or subtract whatever our value for our critical value is. multiplied by the square root of our population standard deviation for the first group of 6 squared all over the sample size of 36 plus the standard deviation of the second squared, which is 5, all over the sample size of the second sample, which is 36. And we have all of our values. Let's take care of everything underneath the radical as well as everything that's in our parentheses on the left there. So 65 minus 15 minus 50, we get 15 plus or minus 1.96 multiplied by the square root of that huge mess there. Okay, so 6 squared gets you 36. So we have 1 plus 25, which is 5 squared, over 36. That's equal to 0.694 repeating. Adding those two values together, we get 15 plus or minus 1.96, square root of 1.694 repeating. Taking the square root of that value, we get 1.30 about. Okay. Multiply that 1.30 by 1.96. This one might be a little bit more accurate because I didn't round it. I just used whatever the output was for the calculator. But I got 2.55 there, which means that we're going to be working with these calculations for our confidence interval. 15 minus 2.55 is 12.45, and 15 plus 2.55 is 17.55. Okay, and that is our confidence interval for our problem. I'm going to leave it here for a second so that you see all the work together, and that concludes our